we see no evidence of any of them in the galaxy at all. So the paradox is why?
And the size of the galaxy and the fact that the galaxy has been around a long time, that there's plenty of time for
frequencies to be at the right time, looking at the right place.
All this has to come together.
Right. Now,
look into the Milky Way and the first impression is abundance. Stars crowd the sky, planets circle most of them. The raw materials of chemistry are everywhere we have learned to look. Yet the only technological activity we can confirm is here, on one small world, during one very recent moment in cosmic history. That contrast is the Great Silence. It is not proof that Earth is alone. It is an observation. No verified extraterrestrial signal, artifact, probe, or engineered structure has yet entered the scientific record. The silence becomes unsettling only when we place it beside time. Our galaxy is more than 10 billion years old. The Sun is less than half that age. Many planetary systems had billions of years before Earth existed. Enrico Fermi compressed the tension into a famously short question: where is everybody? The modern Fermi Paradox is not a mathematical contradiction. It is a mismatch between expectation and evidence. If technological life is common, old, and capable of spreading or signaling, some trace might seem likely. But the sky has offered no trace that survives careful scrutiny. There are many possible resolutions. Perhaps life is rare. Perhaps intelligence is rare. Perhaps technology destroys itself, becomes quiet, or looks nothing like our expectations. Perhaps the simplest answer is that our search has barely begun. Each possibility changes what the silence means. None has yet won. So this investigation begins with a discipline. Separate what is observed from what is imagined. The silence is observed. Almost everything offered to explain it remains inference, theory, or speculation. For most of human history, planets beyond the solar system were reasonable guesses. Now they are measured worlds. Space telescopes watch stars dim as planets cross their faces. Spectrographs detect the small gravitational pull of unseen companions. Thousands of exoplanets are confirmed, and the catalogue keeps changing our sense of what is ordinary. Rocky planets exist. Some orbit where temperatures could permit liquid water under suitable conditions. Water, carbon chemistry, and organic molecules are not peculiar to Earth. They occur in meteorites, comets, planetary atmospheres, and interstellar clouds. These are observed facts. They show that ingredients and environments can be widespread. They do not show that life inevitably begins. Earth supplies one provocative clue. Geological evidence suggests life appeared relatively early after the planet became persistently habitable. That may mean biology starts readily when conditions allow, or it may reflect a selection effect. Observers can only arise on a world where life began early enough to evolve complexity. One example cannot reveal a cosmic rate. The Drake equation is useful here but often misunderstood. It multiplies factors: the rate of star formation, the fraction with planets, the fraction of potentially habitable worlds, then increasingly uncertain steps from life to intelligence, detectable technology, and the duration of that detectable phase. It is a framework for organizing ignorance, not a prediction machine. Astronomy has improved several terms on the left side. Biology and sociology dominate the right. Depending on assumptions, the same equation can describe a crowded galaxy or an empty one. That flexibility is not a failure. It identifies exactly where evidence is missing. Distance makes the galaxy feel unreachable. Light itself needs about 100,000 years to cross the Milky Way. Human spacecraft are vastly slower, but the relevant comparison is not a human lifetime. It is the age of the galaxy. Imagine a civilization sending slow probes to nearby stars. Each destination eventually launches new probes. No vessel needs impossible speed, and no traveler needs to cross the whole galaxy. The expansion is a relay. Even with long pauses between journeys, theoretical studies find that a spreading wave could cross the galaxy in a small fraction of its age. often millions to hundreds of millions of years, depending on the assumptions. Self-replicating probes sharpen the idea. A machine arriving in another system could use local material to build descendants. This is a theoretical possibility, not an observed technology. It may be impractical, undesirable, or unstable. Yet if it works even once, multiplication changes the timescale. Nor must expansion resemble biological colonization. Long-lived instruments could map stars, alter asteroids, capture energy, or leave waste heat. A civilization might rearrange only a few systems. Given enough time, even modest engineering might create patterns unlike natural astrophysics. This is why the paradox is more than a complaint about unanswered radio messages. If one old technological lineage expanded and persisted, why is the galaxy not visibly altered? The argument contains assumptions that expansion is possible, that someone chooses it, that traces endure, and that we would recognize them. Any one may fail, but together they turn silence into a real scientific puzzle rather than a slogan.
Civilization to rise up, send out a mission to multiple planets, pitch tent, use local resources to build more rockets and go to 2 planets, 4, 8, 16. You can do this in hundreds of millions of years, easily.
Right.
Without even warp drives or anything, right?
1/10 the velocity of light.
1/10 the speed of light.
Right.
Very modest for any modern civilization.
Yes.
Still not us. We're not in that category yet. And if that's the case, the galaxy could and should be teeming with alien civilizations. So where are they? What's the...
The first answer is also the starkest. Perhaps there is almost nobody to find. Earth is not merely a rocky planet with water. Its history combines a long-lived star, a stable orbit, active geology, a protective atmosphere, cycling elements, and billions of years without permanent sterilization. Some proposed requirements may be essential, others may be incidental. The rare Earth idea is a supported line of inquiry, not a settled checklist. Then come the biological transitions. Life began with simple cells. Complex cells containing specialized internal machinery appeared much later. Multicellular organisms took longer still. Brains, language, cumulative culture, and industrial technology are not a single ladder. Evolution has no obligation to produce them. On Earth, bacteria dominated for most of life's history. Many successful species never needed technology. Intelligence also carries costs. Large brains consume energy, long childhoods require care, and sophisticated behavior depends on bodies and environments that can exploit it. The fact that one lineage built radio telescopes does not show that this outcome is common. Perhaps the origin of life is the rare step. Perhaps simple life is common but complex cells are the bottleneck. Perhaps technological intelligence requires a chain of contingencies so unlikely that most living planets remain quiet forever. With a sample size of 1 biosphere, we cannot rank these possibilities confidently. That uncertainty makes nearby biology unusually important. Independent life on Mars, Europa, Enceladus, or Titan would imply that biology began more than once in one planetary system. If it shares Earth's ancestry, the lesson is narrower. If it represents a second origin, one unknown term in the cosmic equation would change dramatically.
So who knows whether we should go that far? But I think civilizations are very rare. And I think it's the biology. So I'm guessing, I'm giving you a guess. I'm saying that in my opinion, I think there's one civilization in the Milky Way galaxy and there only has ever been one, and there might only ever be one, and that's us. Which, by the way, means that we have a tremendous responsibility not to mess this up. Because as I said I was asked to give a video introduction to the climate summit, the COP26 climate summit in Glasgow recently. Give the world leaders 1 minute. They said, you've got a video, say something to them. And I said, I think, let's assume that we're the only civilization currently in the Milky Way galaxy. Perhaps the only civilization there will ever be. That means the Earth is the only island of meaning in a sea of 400 billion suns. And so if we destroy this, we might...
The great filter gives the rarity argument a disturbing shape. Between lifeless matter and a civilization capable of spreading through space lies a sequence of steps. If the galaxy is quiet, at least one step may be extraordinarily difficult. That step is the filter. It could lie behind us. Maybe the origin of self-replicating chemistry is almost impossible. Maybe complex cells are the exceptional transition. Maybe the leap from animal intelligence to cumulative technological culture happens on almost no worlds. If humanity has already passed the hardest barrier, the silence is lonely but not necessarily ominous. Or the filter could lie ahead. Technological species may repeatedly acquire dangerous power before acquiring the judgment to control it. Nuclear war, engineered pathogens, environmental instability, and poorly controlled artificial intelligence are different risks, not one inevitable script. Science cannot infer that every civilization destroys itself. It can say that some technologies create global failure modes. The filter may not be a single catastrophe. It might be a long statistical corridor, resource limits, political fragmentation, declining ambition, or repeated setbacks that prevent durable expansion. A civilization could survive while never becoming visible across interstellar distances. Evidence can move our assessment in uncomfortable directions. Finding simple life nearby but no complex life might suggest that life's origin is easy and later transitions are hard. Finding complex life in many places would push the suspected barrier closer to intelligence or technology. None of those discoveries would prove a future disaster. They would update probabilities in a model with profound uncertainty. The Great Filter is therefore not a prophecy. It is a warning against assuming that surviving one stage guarantees the next. The key question is not merely whether a barrier exists. It is which barrier the universe has already revealed and which one remains hidden.
Away to the nearby solar system, 4 light years in our case to Alpha Centauri, but you can't build spacecraft that can traverse a galaxy. That's a possibility. One of the arguments against that for me is the argument, it's called the space travel argument against the existence of extraterrestrial life. And it's often framed in terms of self-replicating machines, so-called von Neumann machines. So imagine it's possible for us, for a civilization, to build a machine, some kind of AI, that's sufficiently smart and capable that it can fly to a nearby solar system, reproduce itself, copy itself, and then send the copy out to the next solar system.
Detection depends not only on how many civilizations arise, but on how long they remain detectable. This is the final term in the Drake equation, and it may dominate the answer. Earth has leaked strong radio and television signals for only a tiny interval. Even that leakage is changing as communication becomes directional, digital, and cable-based. Powerful radars remain visible in principle, but they sweep limited regions at limited times. An observer must be in the beam, listening at the right frequency during the right year. A technological society might endure for 1 million years while its obvious radio phase lasts only a century. It could move to efficient networks, tight beams, or communication methods we have not conceived. Silence would then measure a short detection window, not a short civilization. Extinction is another possibility, but it requires care. War, ecological damage, pandemics, asteroid impacts, and technological accidents are supported risks. Universal self-destruction is speculation. Civilizations may become more resilient, distribute themselves across habitats, or develop institutions that reduce danger. There is also a middle ground between flourishing and extinction. A society might lose the capacity for large engineering projects. It might choose stability over growth. It might turn inward, fragment, or simply stop transmitting. Archaeological technosignatures could outlive it, but only if we know where and how to look. The overlap problem is severe. 2 technological species can inhabit the same galaxy yet miss each other by millions of years. Their signals pass through empty space. Their artifacts erode or become indistinguishable from nature. Cosmic time is generous for expansion, but unforgiving for conversation. Every search begins with an image of its target. That image can become a trap. Early SETI concentrated on narrowband radio because radio crosses interstellar space efficiently, and narrowbands can be difficult for nature to produce. That remains a strong method. It is not the only conceivable method. Pulsed optical lasers, infrared waste heat, Unusual atmospheric chemicals or artificial structures could reveal technology without a greeting. Advanced engineering may not scale as science fiction expects. A civilization could become efficient rather than extravagant. It might compute in cold environments, build below surfaces, or use energy in ways that produce weak signatures. Its machines may be microscopic, distributed, or transient. These are theoretical possibilities, offered to widen the search rather than describe known aliens. Deliberate silence is more speculative. The zoo hypothesis imagines observers who avoid interference. The dark forest idea imagines concealment driven by fear. Neither currently offers testable evidence, and neither should be treated as established science. They explain almost any silence too easily. There are simpler reasons not to broadcast. Interstellar messages are slow. A reply across 1,000 light-years takes at least 2,000 years for a round trip. Targeted transmissions cost energy and require patience. A civilization may transmit only toward worlds it already considers interesting. Our own assumptions are visible in our instruments. We favor frequencies we can use, signal structures we can process, and timescales we can fund. An alien technology need not violate physics to escape those filters. It need only occupy a part of possibility space we have not sampled.
Left over from that today,
All of that based on this assumption.
that you're not special. And you get all of that. And then this prediction was that there'd be microwave background radiation left over from the Big Bang of 5 degrees. And I worked with Penzias and Wilson in graduate school, did a project with them. I observed on
They
the
got the Nobel
telescope.
Prize for that first measurement.
They discovered the microwave background, 2.7 degrees. This is like predicting that
The phrase "we have searched" conceals a vast number of coordinates. Where in the sky? Which stars? At what frequencies? With what bandwidth, sensitivity, repetition rate, and duration? Were we looking for a continuous beacon, a brief pulse, drifting tones, images, heat, or chemistry? SETI researchers describe this as a cosmic haystack. A complete search would cover position, distance, time, frequency, polarization, modulation, power, and many kinds of signal. Real surveys occupy thin slices of that multidimensional volume. The ocean analogy makes the scale intuitive. If the entire search space were Earth's oceans, historical radio searches have sampled something closer to a glass of water than a meaningful fraction of the sea. Exact comparisons depend on how the haystack is defined, but the conclusion is robust. Coverage is tiny. That does not make past searches pointless. Each observation rules out certain transmitters above certain powers in certain directions at certain times. Modern projects observe more stars, wider bands, and larger data streams. The Allen Telescope Array, Green Bank Telescope, Meerkat, and other facilities can conduct targeted and commensal searches. New algorithms can revisit archived observations, but non-detection must be stated precisely. It means a particular instrument did not find a qualifying signal in a specified search. It does not mean the galaxy contains no technology. This is the specialist's corrective to the drama of the paradox. The silence may be deep. Our listening has been shallow. Both statements can be true.
That equal to the volume of the Earth's oceans.
Okay.
All that water. So how much have we sampled in the last 50 years? 1 12-ounce glass. It's not a lot. And so if you were looking for fish in the ocean, are there any fish in the Earth's ocean? Here's a glass. I'm gonna scoop up a glass and I'm gonna look at it. And there aren't any fish in there. Can you claim that there are no fish in the ocean?
Yeah, you'd be stupid to do so.
A genuine discovery would begin with elimination. Radio observatories reject terrestrial interference, satellites, aircraft, and instrumental artifacts. A candidate should repeat or behave consistently with a fixed point on the sky. Independent observatories should confirm it. Extraordinary interest does not lower that standard. Narrowband radio remains attractive because natural sources rarely compress power into extremely fine frequency ranges. A drifting tone could reflect acceleration on a rotating or orbiting world. Short laser pulses could briefly outshine a star at one wavelength. Neither signature automatically proves intelligence. Both demand verification. Technosignature searches now extend beyond messages. Industrial gases in an exoplanet atmosphere might be difficult to maintain naturally. Artificial illumination could alter a planet's night-side spectrum. Large orbiting structures might create unusual repeated transit shapes. Extensive energy use could appear as excess infrared heat. Each proposal must first survive ordinary astrophysical explanations. Biosignatures ask a different question. Oxygen, methane disequilibrium, pigments, or seasonal atmospheric changes might suggest biology without technology. A biosignature could reveal microbes. A technosignature implies purposeful or industrial activity. Both can produce false positives, so context matters. No single strange light curve, unexplained burst, or chemical anomaly is aliens by default. The productive response is not dismissal or celebration, it is better data. Multiple methods should converge on an explanation that natural processes cannot reasonably supply. The first confirmed evidence may be ambiguous at first, a pattern that repeats, a spectrum that resists geology, or an engineered object found close to home. Discovery would likely be a process, not a cinematic moment.
Solely on looking at radio frequencies, because that's what we could imagine another civilization having the capability of using. Charlie Towns, who invented the laser, early on said, send laser pulses, and many people said that's ridiculous. Another civilization, even very advanced, wouldn't have the capability of doing it. Now that we have the capacity ourselves, it's very imaginable that another civilization could do it as well. So now the search for extraterrestrials using electromagnetic radiation uses both radio signals and also looks for brief laser pulses. So in
this
part,
is a matter of decades.
And this is a matter of just a few decades. And so it's really a question of coming up with a systematic way of searching for some phenomena that we can very clearly specify. You know, if we want to rule out the possibility that there is a nanoprobe somewhere in the solar system.
The universe is old, but its habitable era may be young. Small red stars can burn for trillions of years, vastly longer than the current age of the cosmos. If planets around some of those stars remain suitable, most opportunities for life may lie in the future. This does not prove that humanity arrived early. Red dwarf environments bring complications: stellar flares, tidal locking, atmospheric erosion, and uncertain long-term habitability. Yet the timescale changes the intuition behind the paradox. We compare ourselves with the past because the past is all we can observe. Cosmic biology may be weighted toward ages that have not happened. Heavy elements also accumulated over generations of stars. The earliest universe lacked the chemical inventory for rocky planets and complex chemistry. Later epochs produced more suitable material, while changing radiation and star formation conditions. There may be a broad window in which technological life becomes increasingly possible and then eventually declines. If that window extends trillions of years, being among the first is less extraordinary than it appears from today's calendar. The Milky Way can be ancient while technological civilization remains rare now. There is another selection effect. Any species asking this question necessarily appears at a time when its own star and planet permit observers. From one observation, we cannot tell whether our timing is typical. We are early is a theoretical possibility, not an escape clause. Still, it offers a different emotional reading of the silence. An empty sky need not be a graveyard, it could be a dawn. After every proposed solution, the evidence remains asymmetric. We know that planets are common. We know that chemistry is widespread. We know that life and technology exist at least once. We do not know how often life begins, how often it becomes complex, how often intelligence builds technology, or how long detectable activity persists. We have no confirmed extraterrestrial technosignature that is observed. From it we can support limited inferences. Bright, persistent, nearby technologies of certain kinds are not obvious in the data examined so far. Claims that nobody exists, that everyone self-destructs, or that aliens are hiding go beyond the evidence. The Fermi Paradox survives because several reasonable ideas pull in opposite directions. The galaxy offers enormous numbers of worlds and enormous spans of time. Expansion appears possible without exotic physics. Yet biological evolution may contain rare steps, technological windows may be brief, and our surveys cover only a minute's search space. The next evidence may come from an exoplanet atmosphere, an icy moon, a disciplined radio survey, an optical pulse, or an astronomical anomaly that refuses every natural explanation. It may also remain absent for generations. Either outcome teaches us only if the search is measured honestly. So where is everybody? The most accurate answer is not nowhere. It is not yet detected. Those words preserve the difference between silence and emptiness. The paradox does not prove that aliens do not exist. It exposes a gap between what feels statistically plausible, what instruments have actually observed, and how little we understand about life's path from chemistry to civilization. For now, the Milky Way remains both crowded with possibility and silent in evidence. We listen because either answer would change our place in nature. If another intelligence is found, the universe has produced company. If the search continues to find only us, then consciousness may be rarer and more consequential.